In nuclear science, the decay chain refers to the radioactive decay of different discrete radioactive decay products as a chain series of transformations. They are also known as radioactive cascades. Most radioisotopes do not decay directly to a stable state, but rather undergo a series of decays until eventually a stable isotope is reached. Decay stages are referred to by their relationship to previous or subsequent stages. A parent isotope is one that undergoes decay to form a daughter isotope. One example of this is uranium decaying into thorium. The daughter isotope may be stable or it may decay to form a daughter isotope of its own. The daughter of a daughter isotope is sometimes called a granddaughter isotope. The time it takes for a single parent atom to decay to an atom of its daughter isotope can vary widely, not only for different parent-daughter chains, but also for identical pairings of parent and daughter isotopes. While the decay of a single atom occurs spontaneously, the decay of an initial population of identical atoms over time t, follows a decaying exponential distribution, AIT, where I is called a decay constant. Because of this exponential nature, one of the properties of an isotope is its half-life, the time by which half of an initial number of identical parent radioisotopes have decayed to their daughters. Half-lives have been determined in laboratories for thousands of radioisotopes. These can range from nearly instantaneous to as much as 10-19 years or more. The intermediate stages each emit the same amount of radioactivity as the original radioisotope. When equilibrium is achieved, a granddaughter isotope is present in direct proportion to its half-life. But since its activity is inversely proportional to its half-life, each nuclide in the decay chain finally contributes as much radioactivity as the head of the chain, though not the same energy. For example, uranium-238 is weakly radioactive, but pitchblende, a uranium ore, is 13 times more radioactive than the pure uranium metal of the same amount because of the radium and other daughter isotopes it contains. Not only are unstable radium isotopes significant radioactivity emitters, but as the next stage in the decay chain they also generate radon, a heavy, inert, naturally occurring radioactive gas. Rock containing thorium and/or uranium emits radon gas that can accumulate in enclosed places such as basements or underground mines. Radon exposure is considered the leading cause of lung cancer in non-smokers. History: all the elements and isotopes we encounter on Earth, with the exceptions of hydrogen, deuterium, helium, helium-3, and perhaps trace amounts of stable lithium and beryllium isotopes which were created in the Big Bang, were created by the S process or the R process in stars, and for those to be today a part of the Earth, must have been created not later than 4.5 billion years ago. All the elements created more than 4.5 billion years ago are termed primordial, meaning they were generated by the universe's stellar processes. At the time when they were created, those that were unstable began decaying immediately. All the isotopes which have half-lives less than 100 million years have been reduced to 0.000000000000028% or less of whatever original amounts were created and captured by Earth's accretion. They are of trace quantity today, or have decayed away altogether. There are only two other methods to create isotopes: artificially, inside a man-made reactor, or through decay of a parent isotopic species, the process known as the decay chain. Unstable isotopes are in a continual struggle to become more stable. The ultimate goal is becoming one of the 200 or so stable isotopes in the universe. Stable isotopes have ratios of neutrons to protons in their nucleus that start out at 1 in stable helium-4 and smoothly rise to 1.5 for lead. The elements heavier than that have to shed weight to achieve stability, most usually is alpha decay. The other common method for isotopes of the proper weight but high NP ratio is beta decay, in which the nuclide changes elemental identity while keeping the same weight and lowering its NP ratio. Also there is an inverse beta decay, which assists isotopes too light in neutrons to approach the ideal. However, since fission almost always produces products which are neutron-heavy, positron emission is relatively rare compared to beta emission. There are many relatively short beta decay chains, at least 2 for every discrete weight up to around 207 and some beyond, but for the higher weight elements there are only 4 pathways in which all are represented. This fact is made inevitable by the 2 decay methods possible, alpha radiation, which reduces the weight by 4 AMUs, and beta, which does not change the weight at all. The 4 paths are termed 4N, 4N plus 1, 4N plus 2, and 4N plus 3. The remainder of the atomic weight divided by 4 gives the chain the isotope will use to decay. There are other decay modes, but they invariably occur at a lower probability than alpha or beta decay. 3 of those chains have a long-lived isotope near the top. They are bottlenecks in the process through which the chain flows very slowly, and keep the chain below them alive with flow. The 3 materials are uranium-238, uranium-235 and thorium-232. The 4th chain has no such long-lasting bottleneck isotope, so almost all of the isotopes in the chain have long since decayed down to very near the stability at the bottom. Near the end of the chain is bismuth-209, which was long thought to be stable. Recently, however, B209 was found to be unstable with a half-life of 19 billion years. It is the last step before stable thallium-205. In the far past, around the time that the Solar System formed, there were more kinds of unstable high-weight isotopes available, and the 4 chains were longer with isotopes that have since decayed away. Today we have manufactured extinct isotopes, which again take their places, plutonium-239, the nuclear bomb fuel, as the major example has a half-life of only 24,500 years, and decays by alpha emission into uranium-235. Types of decay. The 4 most common modes of radioactive decay are, alpha decay, beta decay, inverse beta decay, and isomeric transition. Of these decay processes, only alpha decay changes the atomic mass number of the nucleus, and always decreases it by 4. Because of this, almost any decay will result in a nucleus whose atomic mass number has the same residue mod 4, dividing all nuclides into 4 chains. The members of any possible decay chain must be drawn entirely from one of these classes. All 4 chains also produce helium-4. 3 main decay chains are observed in nature, commonly called the Thorium Series, the Radium or Uranium Series, and the Actinium Series, representing 3 of these 4 classes, and ending in 3 different, stable isotopes of lead. The mass number of every isotope in these chains can be represented as A equals 4N, A equals 4N plus 2, and A equals 4N plus 3, respectively. The long-lived starting isotopes of these 3 isotopes, respectively thorium-232, uranium-238, and uranium-235, have existed since the formation of the Earth, ignoring the artificial isotopes and their decays since the 1940s. Due to the quite short half-life of its starting isotope neptunium-237, the 4th chain, the Neptunium series with A equals 4N plus 1, is already extinct in nature, except for the final rate-limiting step, decay of bismuth-209. The ending isotope of this chain is now known to be thallium-205. Some older sources give the final isotope as bismuth-209, but it was recently discovered that it is radioactive, with a half-life of 70265995944000000 unregistered trademark 1.9A, 10-19 years. There are also non-transuranic decay chains, for example those of magnesium-28 and chlorine-39. On Earth, most of the starting isotopes of these chains before 1945 were generated by cosmic radiation. Since 1945, the testing and use of nuclear weapons has also released numerous radioactive fission products. Almost all such isotopes decay by either beta or beta plus decay modes, changing from one element to the another without changing atomic mass. These later daughter products, being closer to stability, generally have longer half-lives until they finally decay into stability. Actinide alpha decay chains. In the 4 tables below, the minor branches of decay are omitted. The energy release includes the total kinetic energy of all the emitted particles and the recoil nucleus, assuming that the original nucleus was at rest. The letter A represents a year. In the tables below, the historic names of the naturally occurring nuclides are also given. These names were used at the time when the decay chains were first discovered and investigated. From these historical names one can locate the particular chain to which the nuclide belongs, and replace it with its modern name. The three naturally occurring actinide alpha decay chains given below are thorium, uranium radium, and actinium are each ends with its own specific lead isotope. All these isotopes are stable and are also present in nature as primordial nuclides, but their excess amounts in comparison with lead-204 can be used in the technique of uranium-lead dating to date rocks. Thorium Series equals. The 4N chain of Th232 is commonly called the Thorium Series, or Thorium Cascade. Beginning with naturally occurring thorium-232, this series includes the following elements: actinium, bismuth, lead, polonium, radium, and radon. All are present, at least transiently, in any natural thorium-containing sample, whether metal, compound, or mineral. The series terminates with lead-208. The total energy released from thorium-232 to lead-208, including the energy lost to neutrinos, is 42.6 MeV. Neptunium series equals. The 4N+1 chain of Np237 is commonly called the Neptunium series, or Neptunium Cascade. In the series, only two of the isotopes involved are found naturally, namely the final two, bismuth-209 and thallium-205. A smoke detector containing an americium-241 ionization chamber accumulates a significant amount of neptunium-237 as its americium decays. The following elements are also present in it, at least transiently, as decay products of the neptunium: actinium, astatine, bismuth, francium, lead, polonium, protactinium, radium, thallium, thorium, and uranium. Since this series was only studied more recently, its nuclides do not have historic names. One unique trait of this decay chain is that it does not include the noble gas radon, and thus does not migrate through rock nearly as much as the other three decay chains. The total energy released from californium-249 to thallium-205, including the energy lost to neutrinos, is 66.8 MeV. Uranium series equals. The 4N+2 chain of U-238 is called the Uranium Series, or Radium Series. Beginning with naturally occurring uranium-238, this series includes the following elements: astatine, bismuth, lead, polonium, protactinium, radium, radon, thallium, and thorium. All are present, at least transiently, in any natural uranium-containing sample, whether metal, compound, or mineral. The series terminates with lead-206. The total energy released from uranium-238 to lead-206, including the energy lost to neutrinos, is 51.7 MeV. Actinium series equals. The 4N+3 chain of uranium-235 is commonly called the Actinium series, or plutonium cascade. Beginning with the naturally occurring isotope U-235, this decay series includes the following elements: actinium, astatine, bismuth, francium, lead, polonium, protactinium, radium, radon, thallium, and thorium. All are present, at least transiently, in any sample containing uranium-235, whether metal, compound, or mineral. This series terminates with the stable isotope lead-207. The total energy released from uranium-235 to lead-207, including the energy lost to neutrinos, is 46.4 MeV. Beta decay chains in fission products. Since the heavy original nuclei always have a greater proportion of neutrons, the fission product nuclei almost always start out with a neutron-proton ratio significantly greater than what is stable for their mass range. Therefore they undergo multiple beta decays in succession, each converting a neutron to a proton. The first decays tend to have higher decay energy and shorter half-life. These last decays may have low decay energy and/or long half-life. For example, uranium-235 has 92 protons and 143 neutrons. Fission takes one more neutron, then produces 2 or 3 more neutrons. Assume that 92 protons and 142 neutrons are available for the two fission product nuclei. Suppose they have mass 99 with 39 protons and 60 neutrons, and mass 135 with 53 protons and 82 neutrons, then the decay chains can be found in the tables below. See also, nuclear science, radioactive decay, decay product, radioisotopes. Notes. References: C.M. Lederer, J.M. Hollander, I. Perlman. Table of Isotopes. New York, John Wiley & Sons. External links: Nucleonica Nuclear Science Portal, Nucleonica's decay engine for professional online decay calculations, decay chains, government website listing isotopes and decay energies, National Nuclear Data Center freely available databases that can be used to check or construct decay chains. Fully referenced. The live chart of nuclides, IAEA with decay chains, Decay Chain Finder.